All right. Good morning and welcome back. So we had quite a bit of technical troubles earlier and technical difficulties, and I hope things are going to work out today. So this class has been long overdue actually. All right, and as the title of the stream suggests, we are going to discuss one of the fundamental concepts built in within the analysis of frequency response, the way we study frequency responses. Okay. All right. So I would wait here for 2 more minutes as usual, so that more people can join, and then we shall start our discussion here. And as usual, whenever you have any doubt regarding anything we are discussing, please post them on the live chat. I'll be definitely answering your questions. All right. Right. So far we have discussed how frequencies should be considered in a logarithmic scale, right? Okay. And today we're going to see how power, energy, and amplitudes, these must also be considered in logarithmic scale, just because our perception is logarithmic. Simply because our perception is logarithmic, the way we perceive things is logarithmic. And today we shall have a certain more what should I say, a little bit more in-depth discussion on that. Okay, why our perception is logarithmic on that. Okay, because we shall soon learn that logarithmic scales gives us certain advantage over linear scales for certain scenarios. We shall discuss that. We shall learn that. All right. And I had certain changes in the setup, so please let me know if the audio and video quality is fine. All right. All right. So let's start our discussion today. And right at the onset, I should ask you a question. I should start today's discussion with a question, right? Please let me know in the live chat how many of you have never heard the term decibel. Please let me know in the live chat if you have never heard the term decibel. Right? If you have never heard the word decibel or never heard the term decibel, please let me know. Okay, that should give me an idea of how many of you have never heard the term, that particular term, because that is the term we are going to discuss today. Okay, that is the term we use to measure relative amplitudes, measure relative power, and everything. Okay, and right, I just wanted to know if there is anyone among you who have never heard the word decibel. Okay. And I think there is hardly anyone among you who has never heard the term decibel, right? So all of you have, at least in some context, heard the term decibel, right? Now, let me ask you this. So if you have heard the term decibel, let me ask you this. In what context have you heard the term decibel? In what context have you heard the term decibel? So if you have seen multiple scenarios where you have heard the term decibel, please let me know. But in what context do you usually hear the term decibel? Question is, in what context do you usually hear the term decibel? Again, let me know. Or someone is saying a physics book, right? That's a very funny answer. But let's be real, right? We hear the term, yeah, we usually hear the term decibel in the context of amount of sound, right? The volume of sound, right? Right? So we have restrictions on how much sound we can make, okay, such and such, right? All right. So if you have, if you just crack a firecracker, that might create a sound wave of, say, for example, 80 decibel or 90 decibel, something like that, maybe 100 decibel, right? And that might be hazardous for our hearing, right? Yeah, something like that. So if I now ask you this, what does this term decibel measure? What is that used? What is that term being used in that context, in context of sound? Okay, if I tell you this, okay, I have a sound source that is producing a sound wave, okay, that is generating sound at 70 decibel, and I have another sound source that is generating sound at, say, for example, 90 decibel. Okay, so I have one sound source that is generating sound at 70 decibel, and I have another source that is generating sound at 90 decibel. Question is, what is the difference? I mean, what is it? What are you trying to say actually? Of course, 90 decibel is higher than 70 decibel, right? But what is that? What physical quantity am I measuring, right? Right? Whenever we're talking about measuring something, we need to have a physical quantity. What physical quantity? Sound itself is not a physical quantity, right? But the energy contained in sound might be a physical quantity, right? Yeah, things like that. But please let me know, I mean, what you think is the physical quantity that we measure, or rather we talk about when we talk about decibels in a sound wave. What physical quantity are we measuring? Yeah, frequency is a physical quantity, but we do not measure frequency in decibels, right? Yes, someone is saying loudness, right? Someone is saying loudness. Yes, loudness might be a good idea to, visualize the thing. But the question is, what is loudness? What is loudness? Loudness isn't really a physical quantity. It has some inherent underlying physical quantity that appears to be loudness in our ears, right? What do you think it is? Someone is saying amount of vibration. Again, if you say amount of vibration, you're talking about a physical quantity. But what physical quantity? Yeah, someone has just correctly said that it's the amount of power, right? Not electrical power, but the sound energy, rather I would say sound energy, right? But what are sound waves? Okay, we know that sound waves are elastic waves, right? And these sound waves propagate as pressure waves through any medium, right? Through any medium that supports propagation of pressure waves. For example, on air, okay, whenever I'm talking on, exactly, there is a sound source, what happens is that contracts and elongates, yeah, and that actually travels through the air by the method of contraction and elongation, like that, expansion, right? It contracts and expands the air molecules in certain places, and through that a pressure wave propagates. Like if someone asks you, what are these sensors? Our ears are not sound sensors, our ears are pressure sensors, right? These measure pressure, or rather changes in pressure, okay, that comes through air, right? For example, and sound, what is sound? Sound is nothing but a pressure wave, right? Sound is nothing but a pressure wave. So we measure pressure through our ears, right? So our ears are pressure sensor. Now let me again go back to the same question. What exactly are you trying to say when you say I have a sound source that is producing this much decibel of sound, right? The answer would be, of course, pressure, and in association with that, how much energy that particular wave has, right? So understandably, if I just crack a firecracker, that might have produced a sound of, say, for example, 100 decibel, right? That indicates that it has higher energy than, for example, say me talking, right? I'm talking to you, and that probably is like 50 decibels, for example, say. Okay, if somebody is standing right next to me, my voice might sound like 50 decibels, for example. Of course, if I crack a firecracker and which has a 100 decibel sound, okay, 100 decibel of energy, for example, in it, that of course must have a higher amount of energy. But how much higher? How much higher? We shall learn that today. Okay, and we shall see one of the very important ideas hidden behind these logarithmic scales. Okay. Okay, so let's go into the mathematics and let's discuss this thing in a slightly more rigorous way. Okay, without waving your hands like that. Okay, the unit is, of course, the main unit here is Bell, right? Of course, understandably, it's Bell, and of course, you might have guessed that Bell actually comes from the name of Sir Alexander Graham Bell, right? Alexander Graham Bell, he actually did many things. He did invent many things. Okay, you might have studied. Just look up Alexander Graham Bell in on Wikipedia. And in the United States, you have something one very important company, the Bell Labs. Okay, and many of the modern technologies actually originated from Bell Lab. For example, the C programming language that we use, that's everywhere, came from the Bell Lab. The Unix operating system actually came from the Bell Lab. And there are so many things. For example, this unit itself, yeah, came from the Bell Lab. Many things that we take for granted in control system engineering actually came from the Bell Labs. Okay, so yes, this is named after Sir Alexander Graham Bell, and the unit is Bell, of course. Okay, and when I say decibel, deci is nothing but a SI prefix. Okay, SI prefix. So just like decimeter indicates 1/10 of a meter, decibel would indicate 1/10 of a bell, right? So that's going to be decibel would be 0.1 bell. Yeah, as simple as that. Okay, that deci is an SI prefix, right? And bell in short just written as B. Okay, so 1/10 of a bell is 1 decibel. Okay, understandable, right? So that's fine and all. So of course, with that same logic, I have 10 decibel, that makes 1 bell. Okay, but the thing is, bell is kind of a large unit, right? And we try to avoid bell, so the decibel unit is, I mean, more commonly used. Okay, with that knowledge, let's see what we actually are trying to say in this regard, right? And we shall of course discuss what I in the context of, we shall discuss this in the context of our linear time invariant systems, and in fact any systems. But let's talk about this one in the more general perspective, in the more general context here. Okay, so you have heard the term decibel in the context of sound waves, right? In the context of sound waves, right? But what are sound waves? Sound waves are elastic pressure waves that propagate through any medium. For example, air, right? We are not animals that live in underwater. So yes, sound waves that we hear through our pressure sensors, namely our ears, okay, are basically pressure waves that propagate through air, right? These are pressure waves, right? So what is the fundamental thing that we perceive through our ears? That's the pressure, variations in pressure, right? Variations in pressure, right? Understandably. So we perceive variations in pressure through our ears, right? So let's say I have a sound source that is producing pressure waves, of course, pressure waves, and that has an instantaneous pressure of P, for example, right? At any particular instance, consider our sound wave has a pressure of P, for example, right? That's understandable, right? Okay, all right. So if my sound wave has an instantaneous pressure of P, then my question is simple. Okay, if the instantaneous pressure is P, then what is the instantaneous energy contained in that pressure wave? Okay, so those who recall something from your physics classes, you might recall that if I have a pressure wave or an elastic wave, then the pressure, instantaneous pressure, the square of the instantaneous pressure actually indicates the amount of energy contained in that particular wave. So for example, whenever we are talking about sound wave is a pressure wave, and the energy contained in that sound wave would be proportional to the square of the instantaneous pressure. Okay, instantaneous pressure. All right, that's simple to understand, I think. Okay, there is no difficulty. There is not. It's not difficult to understand, right? All right. All right. But the problem is here is that whenever we are talking or whenever we are generating sound through any sound source, it is highly unlikely that we are going to end up with a single frequency, right? It is highly unlikely that we are going to end up with a single tone or single frequency, right? We are going to end up with a large spectrum of frequency that can be analyzed through Fourier transform, for example, right? And here, in that particular scenario, we just simply write RMS. We check all the individual frequencies, okay, and we square up their pressures. So this is the square of the RMS. So what is PRMS itself? RMS is the square root of the mean of the square. So basically, if I take all the frequencies, all the pressure for all individual frequencies, and just square them up and sum them and take the square root, that gives me the RMS. So RMS kind of is representative of the cumulative effect of all the pressure waves of different frequencies, right? So for example, I am talking here, my vocal cord is producing many different frequencies, right? A large spectrum of frequencies, and each particular frequency is having some amount of energy, right? Some amount of pressure, right? If you just take each individual pressure for all the frequencies and square them up, sum them and take a square root, something like that. So, and of course, and divide it by all the frequencies, something like that. So you get the RMS. So RMS is kind of representative of the entire cumulative effect, right? So we write that. And the energy contained in the wave, contained in this sound wave, is proportional to the square of the RMS pressure, right? Right? That's understood, right? All right. With that said, now let's go back to our discussion of linear systems, linear time invariant systems, right? Earlier we discussed that. Of course, in one of our earlier classes, we discussed this very important idea that if I have a linear time invariant system, okay, if I have a linear time invariant system, and again, these ideas are somewhat associated with the concept of linear time invariant system, right? If we have a linear time invariant system whose frequency response is h omega, and we understand all these terms, I'm not going to discuss all these terms once again, okay, please go back to our previous lectures if you have forgotten everything. And if I excite the system with a pure sinusoid that looks like this, a sine and some frequency, say omega naught t, and say it has some certain phase like that, then the output in the steady state is actually, we proved that in one of our earlier classes, then the output in steady state is also another sinusoid, and except for the fact that it will have a different amplitude and a different phase, right? So if the input is a sine omega naught t plus phi, then the output is going to be something like b sine omega naught t plus, say for example, phi 1. Notice the fact that the frequency will not change, for example, in this particular case, right? So for linear time invariant system, right? And the ratio of the amplitude of the output to that of the input is entirely determined by the amplitude response of the system. And what is the amplitude response? That's simply the amplitude of the frequency response function. And we established all of this, right? And the change in phase, namely the difference in phase in the output with respect to the input, so that's phi 1 minus phi, that's entirely determined by the angle of this complex quantity h omega, which is the frequency response again. So this is called the amplitude response, this is called the phase response, right? Very simple, right? So now what happens is, often we express this kind of a term in decibels. Now this is an absolute scale. We often express this ratio in decibels, or rather in bells, maybe, right? So let me again tell you what I just discussed here. I said that decibel is nothing but a representative of some ratio between two similar physical quantities, right? Now let's go back. Say, for example, I'm saying that I'm talking here right now, and maybe I'm producing a sound wave of 50 decibel. Okay, 50 decibel sound wave. Okay, of course that is kind of representative of the RMS energy. say I'm saying I'm producing a sound wave of 50 decibels, right? That's understandable. But my question is now, what does it actually mean? How much energy, or rather how much total energy or how much instantaneous power is contained with that, contained within that? If that is my question, I have to now go into the definition of that thing, right? So now there are two types of bells or two types of decibels in that, in this regard. One that compares the ratio of power, and one that compares the ratio of one that compares the ratio of power, and one that compares the ratio of amplitudes and pressure quantities, right? For example, these quantities, for example, amplitude, pressure, these are known as field quantities. And then there is something called power and energy. The thing is, instantaneous power, energy, these quantities are proportional to the square of the field quantities. That is the thing you have to remember here. Okay. So these power and energy, these quantities are proportional to the square of the amplitude and pressure. Okay. So you understand, for example, if my field quantity is voltage, for example, the instantaneous power is going to be square, proportional to the square of the voltage, right? If the instantaneous, if the field quantity is, for example, current, for example, in that case, the instantaneous power, energy, all these things will be proportional to the square of the current, right? So yes, so if you take the field quantity, square it up, then proportional to that will be the power or energy quantity, right? So if I say that I have produced 50 decibel, for example, then what am I measuring? This is what I'm measuring. I'm measuring kind of a ratio between A and B, kind of an amplitude, ratio of amplitude. Now what is this A? This is kind of the reference energy, or rather reference power, and this is the power of the sound wave we are producing, right? So in the context of our LTI system, A is going to be the amplitude of the input, right? In the context of our LTI system. Now in the context of sound energy, this is going to be a reference power. Now this reference power is basically the quietest sound that we can actually hear, perceive, right? The quietest sound that we can actually perceive or distinguish. As it turns out that a variation of, we can perceive a variation of 20 micropascals. So, right? So the thing is, the quietest sound that we can hear has a pressure fluctuation of 20 micropascal. So we're saying any other field quantity and will also be proportional. Yes, that's the thing. So for any physical wave or any waveform, okay, or any physical quantity, the energy or instantaneous energy or the power is always proportional to the corresponding proportional to the square of the corresponding field quantity. So this is always true. Okay, instantaneous power, this is always true, that instantaneous power is always proportional to the square of the field quantity. I would just put a mod sign here, that could just keep it generalized, but this is true. Instantaneous power is always proportional to the square of the field quantity. You have just have to figure out the proper field quantity and proper proportionality constant here, right? Because I'm just saying proportional, I'm not saying equal to, right? Of course. So yes, that's true universally, right? You just have to properly figure out. Just one more thing, this is not true in quantum mechanics. Other than that, this is true everywhere else. In all classical physics scenario, this is true. Okay, all right. So now we are saying the minimum amount of pressure change in air that we can perceive as sound is 20 micropascal. Okay, 20 micropascal. Understandable, right? And just to give you an idea, the normal atmospheric pressure, for example, is about 1,000 hectopascal. Okay, this is the normal atmospheric pressure. 1 atm, one atmospheric pressure is about 1,000 hectopascal. Not exactly 1,000. I think it's 1013 hectopascal. Okay, 1013 hectopascal. Okay, that's like approximately 1 into 10. That's like 10 to the power 5 pascal. That's the atmospheric pressure we belong in, right? That's the pressure we are seeing all around us, the atmospheric pressure. And on top of that, that small change, right, 20 micropascal, that small change can be perceived by our ear, right? That's the minimum amount of sound that we can perceive or distinguish. All right, this is understandable, right? So we are saying that for my sound wave, the minimum of the reference, I'm saying this is the reference power or the reference pressure that we can actually, so we are writing small p, huh? The reference pressure that we can perceive is about 20 micropascal. So this amount of pressure variation can be perceived by our ears, right? All right, understandable, not very difficult to understand, I think. All right, and say the pressure wave that I am producing through my vocal cord example, for example, while talking to you, is, for example, say that's PRMS, right? That's something I don't know, but I'm producing such a waveform such that the ratio of energy or ratio of instantaneous power is found to be 50 decibel. Now, if you have an Android phone or any phone, for example, you can always download an app, okay, that can measure the amount of decibel in the sound waves around you. So you can do these calculations by yourself, for example, right? Now, what I'm saying that this is the amount of energy I have, amount of pressure wave I have produced, right? So question is, what is the energy, or rather what is the instantaneous energy that I have produced? I have produced, for example, the instantaneous energy that I have produced as sound is this much, is proportional to PRMS square, okay? And the reference instantaneous energy, okay, I'm saying E reference, is proportional to the square of P reference. That's true. Again, I'm just not putting a mod because these are just real quantities. If these were complex quantities, I would just put a mod and then put a square, right? All right. So what is the ratio? What is the ratio? The ratio is understandably, of course, the E RMS divided by E ref, right? I'm saying energy because you can just always divide it by time and find out the pressure, find out the power, okay? Same thing. I mean, it does not invalidate anything. Or let's just say pressure, power. Same thing. Actually, it does not make any difference. Okay. So I can say this, of course, for example, this ratio. Now, of course, try to understand one simple thing. I would have certain quantities. I would have certain quantities, for example, certain proportionality constants here, right? And I would also have certain proportionality constants here, right? Because whenever I'm saying proportional, if I need to make it turn it into an equal to sign, for example, then I have to put a certain constant here, right? Certain constant here. But if I'm taking the ratio of these two quantities, what happens is that, so if I say, for example, here PRMS is going to be a constant multiplied with pressure RMS, right? Square. And here P reference is going to be same thing. All right, that's understandable. So if I take the ratio of these two quantities, what happens is this constant, actually we have now gotten rid of that constant. So what we essentially get is this P RMS divided by P ref. So that is the first advantage that you should look into. The thing is that we do not really talk about what other physical quantities, what other rather physical nature is associated with it, right? Because whenever we are talking about ratios, what happens? All those proportionality constants that that should be there automatically get cancelled out. So these proportionality constants automatically get cancelled out, right? So I have a square, of course, here. But the proportion, so we are not worrying about the proportionality constant, right? We are not exactly concerned about how exactly the power, instantaneous power of a sound wave is equal to the square of the RMS of the pressure wave. We just need to know that these are proportional. Okay, we don't have to measure everything because that will depend on so many things, like for example the humidity, okay, humidity, the temperature, and so many things. But that nature will not change. That's the idea. Okay, it will always be proportional to the square of the RMS of the pressure, for example, for a sound wave. Okay, but the proportionality constant will change. But it does not matter for us because we are just measuring the ratio. The proportionality constant, whatever it is, as long as it is not zero, of course it is not zero, it is going to cancel out, right? So that's what we have. And now in the decibel scale, so this is the advantage we get when we measure things in terms of ratios, right? It lets us cancel out certain other physical quantities that are associated with it, right? And now decibel scales would give us certain advantage over this simple proportional scale, or rather we are going to see that later on. So with that said, what if I take logarithm on both sides? Take logarithm on both sides. Of course, we are taking the common logarithm, okay, with respect to base 10, of course, that's the common logarithm. So if I make that, and again we are assuming everything is a positive quantity here, PRMS, of course RMS power, and this reference power is also an RMS power of the reference. So these are all positive quantities, of course. So in the logarithmic scale, this is going to be the ratio, and yeah, that's the idea. So again, someone is asking, is the constant same for both? Yes, the constant is same for the both, right? Understandably, because for example, right now if you hear the minimum viable sound, of course the proportionality constant will be the same compared if I have a firecracker going off right now, for example, right? So with that said, that's going to be log base 10 on PRMS, sorry, P reference. This is small p, small p is pressure here, and capital P is instantaneous power, and P ref, sorry, we have that, right? No problem, right? No problem, right? So this entire quantity, if I just measure this, for a sound wave, for example, if I measure this gives you how much bell we have for a sound wave. This simply gives you how much bell you have for a sound wave. That's as simple as that. Okay, if I say I have a sound wave of, for example, 10 bells, this is what it is. Okay, right? That is the measurement. But as I said, bell is kind of a large unit, and in order to avoid that, we use a fraction of a tenth of a bell, and a tenth of a bell is called a decibel, right? So if this is a bell, then this is representative of a decibel, right? So this is dB, a decibel, right? Of course 10 decibel would make a bell, right? This entire thing is a decibel now, right? Just put a 10 here, right? So now let's go back to our previous question now. For example, let's go back to our okay, let's do one more step here. Okay, let's do one more step here. Let's notice that here we have a square on both the numerator and the denominator in the index of the logarithm, right? Since we have square on the index of the logarithm on both numerator and the denominator, we can just pull it outside. Say this is PRMS by P ref, and put a square here, and of course by the by the formula of indices inside the logarithm, I can just pull this 2 outside and write it as 20 log 10 by P RMS by P ref, right? All right, that's understandable, right? That's very simple, right? Now, moments ago I said I am measuring, I am trying to figure out what I mean when I say that I am producing a sound wave of 50 decibel. What does it actually mean? What does it mean to produce a sound wave of 50 decibel? Okay, so 50 decibel, so this is again the same thing, right? 50 decibel simply would mean that that quantity 10 log base 10 for that particular sound wave, capital P, instantaneous pressure divided by instantaneous reference pressure. So that quantity, this quantity here, okay, this particular quantity is equal to 50, right? That is what we mean when I say I have a 50 decibel sound wave, right? That's quite understandable, right? Again, if you have any difficulty during the discussion, please feel free to ask in the live chat. All right. But we just moments ago figured out that, again, we just said that P is the power quantity, right? And here for sound wave, the field quantity is the pressure. And in terms of field quantity, this is 20 log base 10 PRMS by PRF, where P is the pressure. This is the field quantity. So instead of writing this here, I can now write this without any objection, I think, right? So this same thing simply indicates that this is 20 log base 10 PRMS, sorry, that's going to be not power RMS but pressure RMS by pressure reference. Of course the 20 simply came because of the fact that we had a square here, right? Instantaneous power is proportional to the field quantity, which is the pressure in this particular scenario. Let's just go back a moment, go back a bit. We have been talking about, yeah, 50 decibel, right? We said 50 decibel. All right. So if you now measure this, if you just take the ratio, of course, so I have log 10 PRMS divided by Pref. Again, this is the pressure quantity. That's going to be 50 by 20, and that's going to be 2.5, right? 2.5. So now we have, if I bring the logarithm to the right hand side, it becomes 10 to the power, right? Common logarithm. So I have pressure reference, sorry, pressure RMS. So this is again the pressure wave that is being produced by myself, right? And this is the reference pressure. In this particular scenario for sound wave, this reference pressure is 20 micropascal. So that is the quietest sound we can hear as normal human beings, right? That's going to be 10 to the power 2.5, right? All right. And just wait a second, I shall bring my calculator up to calculate that. All right. So question is how much is 10 to the power 2.5? That's around 316, right? All right, that's around 316. Okay, all right. So let's write it down. So I have this. I have the fact that pressure RMS divided by pressure reference is around 316. All right. All right. So what I have is PRMS is equal to 316 into P reference. All right. And so as the calculation proceeds is that the pressure wave, the RMS pressure wave I am producing, if I say the sound wave I am producing is of 50 decibel, then this is going to be 316 into 20 micropascal, right? And you can proceed and do the calculation and whatever, right? You can proceed and do the calculation accordingly. But that's not the point here. The point here is never to calculate the exact value. The point is to figure out the ratio. Okay. You can always put the calculation here. Say for example, if I multiply that, it becomes 632 and a 0 into 10 to the power minus 5 Pascal, right? And that should give me somewhere like approximately like 0.06 Pascal. So it is indicative of the fact that if I say I am producing a 50 decibel sound wave, it simply indicates that the pressure wave I am producing, okay, has an instantaneous pressure variation, RMS pressure variation of 0.06 Pascal. It does not mean anything. Actually, if I just tell you this, that I am producing a pressure wave through myself talking here, that pressure wave is of 0.06 Pascal, would it mean anything to you? It wouldn't, right? Probably it wouldn't mean anything to you because I'm talking in absolute scale. But what if I told you this? Because this is the most important point here to note. What if I instead tell you this, that by saying that I'm talking at a 50 the loudness of my voice is 50 decibel, means that I am 316 times as loud as the quietest sound you can hear. Let me again repeat myself. I am producing a sound wave of 50 decibel simply means that the pressure wave I am producing is 316 times stronger, 316 times as strong as the quietest pressure wave that you can hear. Compared to the quietest sound that you can hear through your ears, my voice is 316 times as loud. Now, with that knowledge, you can perceive something, right? You can have an understanding of what I am talking about, right? Because as we discussed in our last class, and we established in our last class that as human beings, we always measure everything in terms of ratio, right? Right? Again, let me just give you another example. Thing will be really properly understood here. For example, now I'm setting off a firecracker, for example, right? For example, again, I just chose 50 decibel because that is a normal human being speaking, and if you're just standing right next to that person, for example, 50 decibel would be a okay measurement, right? If I just if your voice is like mine, then in that case that might be 60 decibel, okay, because I can only shout, for example. Okay, if somebody is shouting, that voice would be like somewhat like 60 decibel and so on, right? But say I just have cracked a firecracker, right? Firecracker. So, and it produced a sound of, say for example, 100 decibel. Okay, but how much is 100 decibel? Let's figure that out, right? How much pressure wave? In terms of the pressure wave, how much was it, right? Right? Because everything is in terms of ratios, right? Let's talk about that. So again, my question is, a normal human voice, if you're standing right next to me, for example, it would be 50 decibel, right? All right. And again, about sound, okay, the energy or instantaneous power of a sound wave decreases proportional to the square of the distance. So the farther you go away from the source, okay, the quieter the sound will become. Okay, that's a different issue altogether. We're not talking about that. But say I just cracked a firecracker and it produced a sound of 100 decibel, for example. So if it produced a sound of 100 decibel, so of course by my calculation I know that in terms of the instantaneous pressure wave it generated, that must be this pre-RMS. So that's the instantaneous pressure it generated compared to 20 micropascal of pressure. So this is the reference, and that's going to be 100. Understandable, quite understandable, right? So with that said, if I say this, that's going to be a 5, right? That's going to be a 5. Understandable, right? Again, very simple. So if I just put this here, so I would have P RMS, again, pressure RMS, right? Divided by pressure reference. And why are we talking about pressure? Because our ears will perceive pressure, right? It won't perceive energy or power. It will perceive in terms of pressure. That's going to be 10 to the power 5. That's going to be 10 to the power 5. So what is 10 to the power 5? It's 1 lakh, right? 100,000, right? So with that calculation, this PRMS, the RMS pressure produced by the firecracker would be all right. So just to again give you an idea in terms of ratio, so I just cracked a firecracker that produced a sound of 100 decibel, right? 100 decibel. What does it actually mean? It means that it created a pressure wave, namely a sound wave, that has a pressure 100,000 times, 1 lakh times as strong as the quietest sound we can hear. So see, just by making it from 50 decibel to 100 decibel, we change it from being a 316 times as strong to 100,000 times as strong, right? And in terms of absolute measurement, if I just put 20 micropascal here, so that calculation is going to be 10 to the power 5 into 20 micropascal, right? That's going to be 2 pascal entirely, right? It's going to be entirely 2 pascal. So the pressure wave that I produce when I talk at 50 decibel is 0.06 pascal, and you can hear me loud and clear, right? And the pressure wave that was produced is 2 pascal, right? You can understand how big it is compared to that, right? All right, is that understood? So with that said, we can now proceed with a very simple understanding here, right? I think you got that, right? All right, but let me just give you the internal idea here. Let's say now I have a even more powerful firecracker, right? Say this firecracker, another firecracker. This is producing a sound wave at 110 decibel. You might say, okay, sir, what is the difference here? Like, I had a firecracker that produced a sound at 100 decibel. Now I have another firecracker that is producing sound at 110 decibel. What is the difference? It's 110 decibel, right? It's 110 decibel, right? All right. So that shouldn't be very different from that. But let's do the calculation. So from our calculation, I have 20 log pressure RMS by pressure reference. That's going to be 110, okay? And here I have said that this is going to be PRMS by PRMS by P ref. Again, the logarithm is with respect to base 10. That's going to be 110 by 20, right? 110 by 20. So that's going to be 5.5. Okay, 5.5. And here, so we have this calculation, P RMS by P reference. That's going to be 10 to the power 5.5, right? And here, this is going to be P RMS equal to 10 to the power 5.5 into P reference, right? All right, understandable, right? There is no confusion here, right? There shouldn't be any confusion here, right? All right. So again, just to go back with our previous calculation, pre-RMS here is 10 to the power 5 into 10 to the power 0.5, right? That's 10 to the power 5.5, right? Into P reference, and 0.5 is square root, so that's going to be this is going to be 10 to the square root, so basically root 10 into 10 to the power 5 P reference, right? That's understandable, no issues with that. All right, so that was the amount of pressure produced when this was 100 decibel, right? But this is the amount of pressure that is produced when this is 110 decibel, right? So this is the amount of pressure that was produced when it was 100 decibel, and this is the amount of pressure it was produced when when this was 110 decibel. So in terms of pressure, like that, something like that, right? But what about in terms of energy? So if I am to measure everything in terms of pressure, for example, in terms of instantaneous power, for example, so this is PRMS. So if I measure everything in terms of power, I have to just square everything up on both sides, right? So if I square everything up and take the square quantity here, so what happens? I get a square here, I get a square here, right? Understandable. That's not difficult to understand. So capital P RMS is equal to, and that was the previous thing, right? That was P RMS for 100 decibel, right? If I square this up, that will be the P RMS for 100 decibel. So what I essentially have here is 10 times power RMS of 100 decibel. Do you know the physical interpretation of that? The very simple physical interpretation is that 110 decibel is not 10% louder than 100 decibel. It is 10 times as loud as 100 decibel. Let that sink in. This is why the decibel scale is very important. 60 decibel is not 20% louder than 50 decibel, but 60 decibel is 10 times as loud as 50 decibel. Similarly, 70 decibel is 10 times as loud as 60 decibel. 80 decibel is 10 times as loud as 70 decibel. And just like that, 110 decibel would be 10 times as loud as 100 decibel. So you get the idea here, right? And just to give you another information here, for example, we measure earthquake in the Richter scale, right? And Richter scale is also a logarithmic scale, like the bell, not the decibel, but like the bell. Okay, and there, if you have an earthquake that has a magnitude of 6 in Richter scale, and if you have, yes, that's capital P, right? And I don't think my handwriting is bad, right? So that's capital P. Yes, we're measuring in terms of power, right? Okay, as I was talking, Richter scale, right? Richter scale is like bell, similar to bell, right? And because of that, an earthquake of 6 point in the Richter scale, okay, the amplitude, the magnitude of the earthquake, okay, and if I compare that with, if I compare a 7 point earthquake, okay, 7 point magnitude in the Richter scale, for example, in an earthquake of 7 point in Richter scale wouldn't be like somewhat larger than a 6 point earthquake, right? No. A 7 point in Richter scale is 10 times as large, or rather 10 times as big in terms of the magnitude compared to a 6 point earthquake in Richter scale, and so on. For example, an 8 point earthquake in the Richter scale would be 10 times as large in terms of the magnitude compared to a 7 point earthquake in the Richter scale. So just if you compare a 6 point earthquake and a 6 point amplitude in the magnitude in the earthquake in the Richter scale earthquake, and 8 point will be 100 times as big, okay, in the magnitude compared to a 6-point earthquake. So you can figure out the difference, right? Because Richter scale is like the bell, right? So a 10-point increase in a decibel, in the decibel scale, means a 10-fold increase in the energy. And similarly, a 1 amplitude increase in the bell, or simply like something like an Richter scale, that would mean again same thing, a 10-fold increase in the amplitude here. A 10-fold increase. You can understand how big that would be, right? So you can't even compare a 6-point earthquake and a 9-point earthquake, right? An earthquake of magnitude 9 in Richter scale would be 1,000 times as large and subsequently 1,000 times as devastating as a 6-point earthquake in the Richter scale, right? And again, just have to make sure that whenever we are using the field quantity, we have to put a 20 logarithm, 20 log base 10, okay? Because yeah, this decibel scale is always measured in terms of the ratio of power. And since instantaneous power is proportional to the square of the field quantity, so if we are talking about the field quantity, we will have a 20 log base 10. And if I am talking about the field power quantity, then I would have a 10 log base 10. And it's always a ratio of the of two similar quantities. All right, so feel free to ask any question that you might have at this point. The idea that you should understand is that decibel scale gives you a logarithmic perception. It puts the logarithmic perception in place, and by that very nature, the total power output of our sun, okay, is 316 decibel, or no, not even that. It's like 306 decibel, I think. Okay. Total power output, total power output of our sun is yes. Someone is saying, is that 10-fold increase? Because yeah, just like that, 10-fold increase simply because that yes, log 10 is just 1, right? Something like that. Yeah, something like that. Very simple calculation, right? Let me just give you that. So hold on. So say I'm saying, say 50 decibels, right? So for example, 50 decibel, right? So 50 decibel is being measured at as 10 log 10 by power here, PRMS divided by P reference, right? All right, something like that. If that's 50 decibel, then of course, if I just make this power 10 times, what happens? Let's see the calculation. Then 10 log this one, if I make the instantaneous RMS power output 10 times as big, then we can use the different things we studied in our schools. Maybe that's going to be 10 into P RMS divided by P reference. And I shall talk about the sun shortly, don't worry. So if I do the calculation here, of course, by means of the logarithm, we have log 10 10 plus log 10 PRMS divided by P ref, right? What is this quantity? That quantity is 1, right? All right. So what is this? This is 10 plus 10 log 10 PRMS by P ref. But how much was this? How much was this? That was in our previous, just our assumption, this was like 50 decibel. So if this is 50 decibel, then what is this entire thing? That's going to be 50 plus 10, right? 50 plus 10, that's going to be 60 decibel. But what is 60 decibel representative of? 60 decibel is representative of 10 times a wave that is 10 times as powerful as the previous example, right? So if I have a pressure wave, for example, that is 10 times, or any waveform, for example, that is 10 times as powerful as a 50 decibel wave, then it is producing a 60 decibel wave. So a 60 decibel is 10 times as much 50 decibel. Something like that, right? So therefore a 10 dB increase, so 10 decibel means 1 bell, right? A 10 decibel increase indicates that tenfold, my head is blocking everything, hold on. So a 10 decibel increase would indicate a tenfold increase in power. Okay, so I think we got that through. 10 decibel increase in sometimes we only talk about amplitudes. By default, everything is measured in terms of power. Just like the thing I was talking about the sun, right? Right. Just to give you the exact calculation, it's 306. Okay. So, for example, the power produced by the sun is like every second, like you can consider the sun to be a very humongous hydrogen bomb, for example, right? It is doing nuclear fission. It is so hot that it is doing nuclear fusion, and it is producing a huge amount of energy, huge, so large that but in the decibel scale, it's simply around 306 decibel. That's the total output power. And if you just calculate it accordingly, it would turn out to be somewhat like 3.8 into 10 to the over 6, 10 to the over 26 watts. This is going to be 3.8 into 10 to the over 26 watts. The same thing, you can do the same measurement, and accordingly you can just keep on calculating the power, instantaneous power. Okay, measure all the calculations, and based on our standard calculations you can figure out that. So you can understand that this is loud, right? Really loud, right? Okay, there is a popular video on YouTube by a channel called Vsauce. You can just go to that, and they have just calculated something very weird. For example, if you can produce a sound wave of, say, for example, 350 decibel, you instantly create something called a black hole. Okay, so if you create a sound wave that's like 350 decibel, it will be like a black hole immediately. You would immediately generate a black hole on Earth. So my point is that using decibel scale, you can measure extremely large quantities and also extremely small quantities, right? The question is, what is 0 decibel? What is 0 decibel? 0 decibel is the difference, right? For example, you can measure the amount of power, for example, here, right? For example, just as a indication here, yeah, the largest quasar, the most powerful object in our universe has a power of instantaneous power of 420 decibel. Quite literally, it's a 420, right? How? Because it's energy, right? The amount of energy that you need, for example. Do you understand what I'm saying here? Okay, the amount of energy. So this is representative of amount of instantaneous energy or instantaneous power, right? Yeah, it's a concentration of energy, right? Concentration of energy. You can understand that if you produce large enough energy, okay, that instantaneously contracts every matter around it, and it will be like an explosion of a black hole, for example. Let me give you even more, even slightly better idea. For example, if you produce, for example, something like 280 decibel, it would be equivalent to exploding one hydrogen bomb. Alright, something like that. It has the same amount of energy. The point is that 350 decibel has the same amount of energy of a black hole. That's the point here. And based on the size of the black hole, it can actually automatically destroy itself, okay, through something called Hawking radiation, and that will actually destroy everything. For example, you can understand what it is, right? This is huge. And that's true the other way around, right? When a nuclear explosion takes place, no, it cannot be possible, right? But just to, I mean, you cannot just make a black hole by producing a sound. But if you could, then this would happen. But the problem is you cannot, right? This is just to give you an idea of how big the units are, how big these units can be, or how small these units can be. Okay, this is yeah. So this is just a representative of how big things can be, right? Of course, you can never produce such a large energy. But let's go back to our early discussion, that we said that, again, let's talk about pressure. So this is, again, in terms of sound, this was 20 micropascal. And if I say I have 0 decibel, question is, what is 0 decibel? What is 0 decibel? 0 decibel simply indicates that if I just take the logarithm outside here, pull it back here. Okay, someone is asking how much a human can create maximum. By speaking or by shouting, right? By shouting, you can go up to like, if you shout very loudly, for example, maybe would be producing somewhat like 80 decibel, maybe, not more than that. Because you have to understand, for example, if I'm shouting, like if I'm talking here, I'm producing 50 decibel, right? 80 decibel would be 1,000 times as much. So yeah, that could be a humane limit there. 80 decibel could be the loudest sound. I don't know whether someone can produce a sound of 80 decibel. I don't know, not entirely sure. All right, so what is 0 decibel in that case? A 0 decibel, if you just divide everything here, so no, you cannot shout that much, right? So you can understand 1,000 times is quite large. That's going to be 0, right? And if I do the calculation here, RMS divided by P reference, I have 20 to the power, so I basically have 10 to the power 0. What is 10 to the power 0? That's 1, right? So pressure RMS by pressure reference, that's going to be 1, right? And the video I talked about, it was quite an old video, not a new one. So right. So whenever, so for example, if you produce a sound wave that has the same pressure as the reference pressure or same energy as the reference energy, then we say it's 0 decibel. So 0 decibel essentially means that the ratio is equal to 1. The ratio is equal to 1. Because if you go back to our very definition here, Yeah, if I say 0 decibel, if I say 0 decibel, 0 essentially means that this is 1, because log 1 is 0, right? So 0 decibel essentially means the output is proportional to the amplitude of the output is proportional to the amplitude of the input, because this ratio, if this ratio is equal to 1, then it's a 0 decibel, right? So 0 decibel is no amplification whatsoever, right? So if you have any query, feel free to ask at this point. All right. Now the point is that in the decibel scale, you can assume the reference as per what you need. Okay, so there are several units. For example, sometimes you probably yeah, of course you have a phone, right? So you sometimes talk about the signal strength, right? So if you have a Wi-Fi or something, you have a you have a corresponding something called a signal strength, right? So you say, okay, I'm not getting network tower right now, or maybe the tower is very poor, signal strength is very poor. We talk about that, right? Signal strength of antennas and things like that. Okay, right? Signal strength. Yeah. Someone is saying, is it possible that hallucination can occur if there is no sound? Actually, yes. Actually, yes. And if I want to discuss that, we will go off beyond our go off track so far that we cannot come back here. Let's keep those discussions for later. Anyway, so let's throw this apart. Let's talk about that the reference quantity we are assuming here could be many things. For example, we have a very popular unit called decibel milliwatt. It's written as dB with a small m. It's called decibel milliwatt, and it simply measures everything in the decibel scale like that. It's 10 log base 10 the power, RMS power, divided by 1 milliwatt. So there is a unit called decibel milliwatt. This is often used to measure signal strength. Okay, decibel milliwatt, for example, and this is quite close to the amount of sound energy that you hear, the minimum quietest amount of sound energy you can hear. Okay, so decibel milliwatt or dBm is the unit that you use to measure signal strength, for example, right? That is the unit you use to measure signal strength, right? For example, the Wi-Fi I'm receiving right now, the Wi-Fi signal that my computer is receiving right now is at, for example, minus 40 decibel milliwatt. So this is the Wi-Fi, this is my Wi-Fi signal strength. Okay, so this is my Wi-Fi signal strength, but question is, what does it actually mean, or how much energy it is receiving from the antenna of the Wi-Fi router to the internal antenna of the Wi-Fi chip inside? So let's understand that. So I'm saying that 10 log 10, because it's a power quantity again, PRMS, this is the energy received by the Wi-Fi signals power, right? This is the power that the Wi-Fi antenna inside my laptop is receiving, right? And compared to 1 milliwatt, this is going to be minus 40 decibel milliwatt. So that's the unit, dBm. dBm stands for decibel milliwatt. Signal strength is usually measured in that. Okay, and again minus 40 decibel, and let's see. So let's calculate that. Let's of course let's forget about the minus unit here, because this has dBm, this has dBm. So let's divide that. I have log base 10 of P RMS divided by 1 milliwatt, and that's going to be -4, right? And if I do the calculation, proceed with the calculation, this becomes P RMS divided by 1 milliwatt, and that's going to be 10 to the power -4. All right. So PRMS, again, PRMS is the power, or rather the signal power the Wi-Fi antenna inside my laptop is receiving from the Wi-Fi router, right? For example, that's going to be 10 to the power -4 into 1 milliwatt. But the question is, what is 1 milliwatt? 1 milliwatt is already 10 to the power -3 watt. So with that calculation, that's going to be 10 to the power -7 watt. Okay. So it's like 100 nanowatt. Okay. So when I say the signal strength is -40 dBm, then I am saying that the amount of energy it is receiving as electromagnetic wave that is being produced by the Wi-Fi router being received by my laptop is 100 nanowatt, for example. So you can understand that 100 nanowatt, how small that is, right? So -40 decibel is like 100 nanowatt, right? And moments ago we talked about the total energy output of the sun, and that was like 306 decibel, right? Okay. So, and that was like 3.8 into 10 to the power 26 watt, right? It's like trillion, something like that. You can understand how big that is, right? So 316 decibel is a huge quantity. -40 decibel is a very small nano level quantity, right? And we can measure all these large variations, okay, using small numbers here. We didn't need to write out such large quantities, right? So in terms of decibel, we have expressed everything like that. Okay, simply keep that in mind, that a 10 decibel increase in terms of power is like 10-fold increase in terms of power, right? All right. So that would be the discussion up to this point. So this is like the introductory discussion, so that you become familiar with what we people actually use the decibel unit for. And decibel unit is everywhere, right? There are so many units like decibel, isotropic, dBi. There are so many units. Okay. The only thing is that the reference value is chosen differently to suit different purposes, right? All right. If you have any question, feel free to ask at this point, and otherwise we shall proceed with our discussion of linear time invariant systems and the frequency response. And before I proceed, there is just one more thing you need to recall. You need to understand that this logarithmic scale is giving me too many advantages, right? There must be some catch, right? Whenever in engineering, everything is a trade-off, right? We gain something and we lose something. Okay, decibel scale is giving me, or rather contracting a very large scale into a very small one, right? So that I can represent very small units effectively, also very large units effectively. But there is one major drawback of the logarithmic scale, is that it cannot represent zero energy, except for the fact that it cannot represent zero energy. So this is the only drawback in this scenario. So this is the only drawback, rather the only drawback of decibel scales or logarithmic scale. That it cannot represent zero. It cannot represent zero. And here I'm saying it cannot represent zero amplitude or zero power or zero pressure or zero frequency, any logarithmic scale would basically fail to represent zero value. Very simple, because it can be understood very simply, because you can understand that I'm saying 10 log, that's the decibel scale, right? 10 log power RMS divided by power reference, right? But if this is zero, if this is zero, then what do I have? I have 10 log, again base 10. I have a 0 here. But what is log 0? Log 0 is negative infinity, right? So yes, you can understand, suitably we cannot represent zero energy, zero power, zero amplitude, zero frequency. These cannot be represented. I can represent as small as I want, but I cannot represent zero. Of course, amplitude, power, pressure, frequency, these are all positive quantities. So there is no point of whether or not we can represent negative quantities. Of course, we cannot represent negative quantities in the logarithmic scale, but we don't need to. But we cannot represent zero quantity, right? That's one of the things you need to remember. We cannot represent zero amplitude, zero power, zero pressure, zero frequency, things like that. We cannot represent zero. 0 decibel means that the power is equal to the reference power, or the pressure is equal to the reference pressure. Amplitude is equal to the reference amplitude. That means we have a 0 decibel. That's the thing. But we cannot represent zero amplitude itself, or zero power itself, or zero pressure itself. That's one of the disadvantages of the decibel scale, of any logarithmic scale rather. With that said, feel free to ask any question that you might have. If it's all clear, let's go back to the frequency response analysis again. Alright, so let's discuss our typical electrical engineering thing, right? So we have a linear time invariant system. And let me tell you, the people who invented these units were indeed electrical engineers, right? Because these things were actually came into context with the context of amplifiers, right? And amplifiers were produced by early control system engineers like H.W. Bode, Nyquist, these people. They were working on amplifiers, and then the discussion on decibel and everything. Someone is saying, how can a vibration blast away? Yeah, the thing is, it's energy, right? So whenever you have a sound wave, it is carrying energy with it, right? It's carrying pressure with it, right? Changes in pressure with it, and that can do various devastating things based on how much pressure you have. So if this is A sine omega naught t plus phi, and the output is B sine omega naught t plus phi 1, and if h omega is the frequency response, then we know that the ratio is ratio of the amplitude of the output sinusoid and the input sinusoid in the steady state would be ratio of h omega. So ratio of the frequency response here, right? And what is the amplitude? Amplitude is a field quantity, right? Amplitude is a field quantity. So in the decibel scale, that's going to be 10 log B by A square, right? Because amplitude is a field quantity, pressure is proportional to the square of the amplitude, so I have a square here, right? So that's going to be 10 log base 10 h omega square all right. So, and if you just take care of the square here, pull it outside, that's going to be 20 log 10 and mod h omega, right? So this is often the amplitude response So this is called the amplitude response. In the decibel scale. Okay, this is known as the amplitude response in the decibel scale. All right, same calculation, same thing, we just put a decibel scale like that. Okay. All right, so let's again go back. Say the frequency response of a, for example, a simple series RC circuit where the output was being measured across the capacitor, for example. It was acting as a low pass filter, for example, and there say for example, again this is just an example, right? This was for example j omega plus a, for example, like that. All right, then of course the amplitude response, this is the frequency response, for example, say, rather not exercise, say example, right? So that would be 1 by root over omega square plus a square, right? Then the amplitude response in decibel scale, so we write it as this in the decibel scale, that's going to be 20 log base 10. Why 20 again? Because we just took a square there, right? 20 log base 10 of mod h omega. All right, so that's again one of the ways we calculate things like that. So we write 20 log base 10, and there we had root over omega square plus a square, and now we would have 20 log base 10 of 1 minus 20 log base 10 on omega square plus a square, right? Again, log 1 is 0, right? So that's 0 minus 20 log base 10 and root over omega square plus a square. All right? All right. The point is, if I just do the calculation here, I mean, I can get rid of the square root, right? Because the square root is nothing but a power of half, right? Power of half, no issues there. Power of half, and with that we have minus 10 log 10 omega square plus a square, because I just took care of the half, power half, by pulling it outside, and that got multiplied with the minus 20 and made it minus 10, right? Right? No issues there, right? No problem. Now, earlier you learned how to do these calculations using a computer, right? But we are talking about 1940s, when people actually invented all these ideas, right? H.W. Bode, H. Nyquist, these people, when they invented these ideas, when they were actually talking, they were actually inventing, they were talking, doing their research, and when they invented amplifiers, you did not have a calculator, right? Let alone a computer, right? You could not do complicated calculations like that. We people only had slide rules, right? Our grandparents, they used only slide rules to do the calculations, right? So you couldn't do much of any complicated calculation with the help of a computer, right? So computers came very late in the scene, let alone calculators, things like that. So with this knowledge, people actually invented certain simplifications that could be very useful in understanding how an amplifier responds to different frequencies. Okay, an amplifier, a filter, a system, these are all interchangeable terms. When I use a system to amplify a signal, it's called an amplifier. When I use a system to, in this system we are talking about electrical circuit, right? Whenever I use an electrical circuit to amplify a signal, it's called an amplifier. Whenever I use an electrical circuit to filter out certain frequencies, it's called a filter. Okay, but the same electrical circuit can serve multiple purposes based on what I intend, what I want it to do, right? So the same terminology, system, amplifier, filter, all this terminology are interchangeable. Okay, interchangeable based on their particular purpose, right? All right, so let's that sink in for a moment, and let's say for this particular example, let's consider an example. Right? Examples are very good. Right? Let's consider A is 10 rad per second, or let's say A is 1 rad per second. Very simple. A is 1 rad per second. So my mod h omega in decibel scale is currently minus 10. So that, let me write it down first. That's going to be 1 by j omega plus 1. Actually, you have plotted the frequency response of this, right? Now we are doing it in decibel scale, and in decibel scale, if I do it in the decibel scale, we are going to have certain advantages. We are going to see that. That's a square, that's 1, right? We have that. Now imagine we don't have a calculator, let alone a computer, let alone Python, for example. Say we have none of these. Okay, and now still I want to plot the frequency response. I have one option. I can do all the calculation manually, right? And do the plotting, but that might be very inefficient. And what if I have a slightly more complicated system than this very simple thing here? Then it will be even more complicated, right? We cannot proceed with that. So people like H.W. Bode, they invented a technique called simplification of frequency response, namely the Bode plot. And we are not going to teach that in this semester, but we shall have just a quick look at that. To do that, let me pull a graph paper. Okay, you have seen this graph paper, right? Our quite familiar graph paper, right? Happy graph paper. All right, you recall that, right? Now say I want to plot the frequency response of this. Okay, in this graph paper, right? All right, hold on. In this graph paper, right? All right, useful. But now we are not going to do any calculation, but we are going to only use simplifications, or rather approximate simplifications here. We are going to approximate things as much as we can. Okay. See, let's take a blacking. The first thing we should do that we should take care of the scale here, right? Again, this is the logarithmic frequency scale we are familiar with, right? And here, of course, you already know that this came from the time constant. This one actually came from the time constant. This time constant is 1. The corner frequency we said is equal to 1. So yes, we are going to see some change at that particular frequency. So the common nomenclature is that we choose frequencies at least 1 decade earlier than the corner frequency and 1 decade later the corner frequency. So we are going to choose frequencies like this. We are going to choose frequency at 0.1 radian per second, and this is going to be 1.0 radian per second. This is going to be 10 radian per second, and that's going to be 100 radian per second, because that's the logarithmic frequency scale, right? That's the logarithmic frequency scale. You have frequency omega in radian per second. That is what you have in that scale, right? Now instead of plotting mod h omega, now here we shall be plotting the h omega in the decibel scale. We are going to plot the h omega in the decibel scale, and you shall see that doing that in the decibel scale would give me a significant advantage over doing this in the absolute scale. If I wanted to do this in the absolute scale, we would have no other way than to just compute everything and plot everything. Okay, but that might not be always suitable, because here in this particular case we have a simple first order system, right? Very simple, a single differential equation of first order, and from that it came like that. But if you have a complicated system, I mean, doing these calculations would take you forever, right? Without using a computer or a calculator at the very least. Now let me just copy paste what I just had here. So this was the calculation we ended up with. All right, this was the calculation we ended up with, and this was the frequency response in the decibel scale. So I don't think there is any issue with that. All right, let's approximate things. One of the fundamental things we do while approximating things, we neglect small quantities, right? Neglect small quantities, right? But what is a small quantity, right? So whenever we do approximation, we neglect small quantities. Just to give you an idea, for example, if I say, for example, if someone says my monthly salary is, say for example, 50,200 rupees. Let's say that. It's a random thing, okay? So you would probably approximate that to say 50,000, right? If somebody says my monthly salary is 50,200 rupees and someone says, okay, approximately 50,000 rupees, that's not a bad approximation, right? We just neglected 200 because 200 would be very small compared to 50,000. But now consider a daily wage earner whose monthly salary, for example, monthly income is, for example, 1,500 rupees, right? Someone who earns 1,500 rupees per month. So are you going to say, not 1,500, maybe 1,400 rupees per month? Question is, are you going to approximate that as 1,000 rupees per month? Someone is saying, I earn 50,400 rupees per month, and you are approximating that to 50,000 rupees per month. That's a good approximation, no problem, because 400 rupees is very small compared to the rest 50,000, right? But if somebody says my income is like 1,400 rupees, and if we approximate that to 1,000 rupees, that would be true to one significant digit. That would be true. Mathematically, it is correct. It's a correct approximation to one significant digit, right? But that's not the point. This is a bad approximation. Whatever you do, it's a bad approximation, right? Even though it's a correct approximation in terms of as far as mathematics goes, okay, it's a correct approximation up to one significant digit. That's true. But it's a bad approximation based on the fact that the term we neglected was quite large, rather comparable with the rest of the term, right? 400 is quite comparable with 1,000, right? But mathematically it was correct. It was not a bad approximation, right? Rather, it was not a wrong approximation, but it was a bad approximation. So here I can consider this to be small. This is small here. This 400 in 50,400 is small, but this 400 in 1,400 is large. So we cannot remove that through an approximation, but we can remove that quantity with an approximation. So what is large and what is small is relative, and we discussed that in our last class, right? What is big and what is small is only relative, right? And that's why all these ratio, relative quantities, approximations, everything is coming into effect, right? So let's get rid of this entire discussion. Rather, let's keep it. Okay, and rather let's pull this calculation here down. Okay, now let's say when omega is small, and how do I determine a small quantity? So let's say when omega is small, say when omega is small. But question is, how would I determine whether or not it's small? I would determine that by comparing omega square with 1. By comparing rather omega with 1, right? So I would say I consider omega to be small. Again, this is just an ad hoc approximation. I would consider omega to be small if omega is smaller than 1, rather smaller than this, rather smaller than a, right? We had a here, if you recall earlier. In this particular, a is equal to 1. So this was supposed to be a, right? Just keep that in mind. Okay. So when omega is smaller than a, in this particular scenario, when omega is smaller than 1, I'm considering that to be small. Okay. Say omega is 0.1 radian per second. Then what is omega square? What is omega square? So it's a quantity smaller than 1. If I square it up, it is going to be even smaller. So it's going to be 0.01. Alright. So my point is, what is omega square plus 1? What is omega square plus 1? That's going to be 1.001, sorry, 1.01. And this can be faithfully approximated to just 1. I think you get the point. 0.01 is quite small compared to 1. Right? I can approximate that to 1, right? Simply, I can do that. So when omega is small, I simply can approximate this entire quantity. Let me just again copy and paste it. Copy pasta. Right. Right. So when omega is small, I can forget about omega. Like that. And I have this. When omega is small, I just have this. So this is now going to be an approximation when omega is small. So when omega is smaller than the corner frequency, particularly A in this scenario. So that is, in this particular scenario, omega is less than 1. I have that approximation. And this value is equal to 0. And the unit is, of course, decibel. Right? We are saying 0 decibel. And let's consider the other situation. When omega is large. Say, when omega is large. But again, what is large? Okay. Here in this particular scenario, we are going to consider omega to be large when omega is greater than equal to, or rather, just let's consider this equal to sign here. It wouldn't change anything, but it would simplify our calculation a bit. I would consider omega to be large if omega is larger than the corner frequency. In this particular scenario, omega is greater than 1. I would consider omega to be large. With the same idea then, if I paste it here, when omega is large, so for example, say omega is, for example, 10. Then what is omega square? Omega square is 100. Then what is omega square plus 1? That's 101. And that can be faithfully represented as 100. But what was this 100? That was just omega square. So when omega is large, I can neglect this plus 1 here. Just like the previous one, when omega is small, when omega was small, I neglected omega itself. And now when omega is large, I'm neglecting 1. That basically that a square, right? Now if I just do the simplification here, that's going to be minus 10 log 10 omega square, and that 2 can come outside, making it minus 20. Okay, something like that. So let's go back to our graph paper. Now we are going to draw a plot of the frequency response without calculating much of anything. And when you actually become familiar with these, what happens is that in order to plot a frequency response, you won't need to do any calculation. For example, I have been doing this for many years, and if you give me a frequency response function, I would probably be able to tell you how the plot looks like roughly without even calculating anything because of these simplifications. Alright, so now this is in a decibel scale, right? This is in decibel scale. Let's say this is, for example, let's say this is this is, say, 0 decibel. This is, say, minus 20 decibel. This is, say, 0 decibel. This is, say, minus 20 decibel. let me just make sure that I end up using the entire page. So that's going to be minus 20 decibel. That's going to be minus 40 decibel. All right. Okay, then you have a very interesting question. I was going to discuss that. What if instead of this question is, what if instead of this I have, so for example, let's go back with the same discussion. If I have h omega with like that, j omega plus a, such that mod h omega is 1 by root over omega square plus a square, right? What if I have something like that? Something like that, right? So again, mod h omega in the decibel scale would, in this particular scenario, would look like minus 10 log base 10 omega square plus a square. Same calculation. Here, the approximation would be something like this. Omega is considered small when omega is less than or equal to a, and subsequently the approximation would be mod h omega in decibel is approximately minus 10 log 10 a square. All right, we will be neglecting omega, and omega is considered large when omega is greater than a. So subsequently the approximation of mod h omega in decibel is going to be minus 10 log 10, and here when omega is large I will be neglecting a. When omega is small I am neglecting omega, and when omega is large I am neglecting a. So that's going to be omega square. So I think I answered your question. Okay. So when this a square is also large, it entirely depends on then the amount of the value at which we consider omega to be small or omega to be large also changes. All right. Right. Let's go back. I think I answered your question. If there is any doubt still, please post it. All right. So we have now seen that when omega is when omega is small, right? When omega was small, that value for this particular example, when omega was small, the value of the amplitude response in this particular example was 0 decibel, right? 0 decibel. Okay. So if I ask you up to what value of omega do I consider the omega value to be small? Up to 1, right? Up to 1 in this particular example, right? So I have these. Try to understand. I have these. I have this as a point in the frequency response plot. Okay. Which says when omega is 0.1 radian per second, the amplitude response is 0 decibel, right? Based on the approximation. Similarly, when omega is 1 radian per second, the amplitude is 0 decibel once more, because the frequency is still considered to be small enough. All right. But what about when omega is 10 radian per second? When omega is 10 radian per second, now it's large, right? When omega is 10 radian per second, it's large. Now this is the value. Now we are going to use that calculation to figure out what is the value when omega is, what is the value of the amplitude response when omega is 10 radian per second. So here, say if I put omega equal to 10, then mod h omega in decibel would be minus 20. Then again, this is an approximation, minus 20 log base 10 and 10 here. So of course log 10 is 1, so that's going to be minus 20 in decibel. All right. So in the decibel scale, now we have that if omega is 10 radian per second, my amplitude is minus 20 decibel, right? Minus 20 decibel. All right. All right. So let's go back again. So this is again omega is large, right? What if omega, instead of being 10, what if omega is 100? This is again the large approximation here. So mod h omega in decibel would approximately be minus 20 log of 100 to the base 10, and log of 100 to the base 10 is 2. So that's going to be minus 40 decibel. So when frequency is 100 radian per second, the amplitude response is minus 40 decibel, right? And this is called an approximation. And what we are going to do throughout this approximation is that we are just going to draw straight lines to join everything. So we have drawn a straight line to join these, and we will draw a straight line to join these. So this is going to be the approximate frequency response. This is the approximate frequency response. Rather, approximate amplitude response. Of course, if you do the correct, proper calculation, if you do the exact calculation, the result would somewhat look like this. Rather, let me just try my best here. Here's the problem, and drawing these things might be very difficult. Yeah, something like that. So this will be the exact calculation. Exact calculation here, and subsequently it will emerge like that. And the black one would be an approximate calculation. But the point here still stands that approximate calculation could be done without doing any computation, right? Very simple, or rather with very simple calculations. But by looking at this amplitude response, question is, can I still say that this system is acting as a low pass filter? Can I still say that this system is acting as a low pass filter? Actually, yes, I can, because as I can see that as the frequency increases, what happens? The amplitude of the output decreases, right? And I can also see that this is subsequently the pass band of the signal. This is the pass band. This is the pass band of the system. Okay, so if the frequency is below this, the gain that the signal receives is 0 decibel. So what is 0 decibel? 0 decibel means the ratio of the amplitude of the output to that of the input is equal to 1. So the signal is passed unaltered by the filter. So this is the pass band, and this is still the stop band. But now with a simplified calculation, yeah, we kind of now say that this is still acting as a low pass filter, right? So this was the idea. When people did not have calculator, like in 1940s, we did not have calculators, we did not have computers, right? So people, or rather scientists, they invented approximate methods to do everything, right? So this is an approximate method to plot frequency response functions, and this has a very proper name, again named after the inventor of this approximation. It is called the Bode plot. So again, he used to work at Bell Labs, okay, H.W. Bode. So this is called a Bode plot. Okay, so this frequency response plot is also known as Bode plot because Bode was the first person to actually discuss these. Okay, so Bode plots are nothing but frequency response plots for LTI systems. So with this, we are going to end our discussion for this entire semester here. And thanks for being here for so many classes and tolerating all these complicated things. All right. And again, we shall have a few more additional classes, but those classes will not be mandatory because we're going to learn a bit of Python programming and employ a few more things here. But none of the questions in your final exam will be from those. So this is going to be the end of our discussion for this entire semester, end of our formal discussion for this entire for our entire semester. And if you face any difficulty regarding anything, I would suggest you that you send me an email. I would definitely be answering your question. And I have given you sample problem sets, so try solving those. With that said, feel free to ask any question that you might have. So I'll be here for just 3 more minutes. Yeah, I have already given you the sample questions. The exam will be based on that. Or rather, I will send you a proper set of sample questions, because I have to update the one that I gave you earlier. Alright. So just as a homework for today's class, I would suggest that you do the Bode plot or this frequency response approximation for a system. So your homework would be this. Draw the approximate Bode plot. So do this frequency response approximation and everything. Yeah, thank you very much for being here and tolerating all the complicated discussions here we have been making. Thank you to all. I should be thankful to you people, right? So let me give you a transfer function, or sorry, frequency response function. And this is, for example, j omega plus 10. My question to you would be that try plotting the same thing here. Okay. I know you don't have a similar graph paper. Yeah, but try at least doing that in your rough paper or whatever. Okay. Try at least figuring out how this plot would look like. In any case, all right, thank you for being here. All right, that's going to be the end of this semester, and hopefully if we are all alive in the next semester, I shall be teaching you control system engineering in the next semester. All right, so with that said, be safe, and we are going to end our discussion today at this point. If you have any query, feel free to ask me via an email. All right, thank you. Be safe.